Okay, so we set up the QSMAT because we saw a specific heat capacity. We got the 60.0 minus the 25.0. All right, so that's getting us 35.0 there. Right, times the 4.18. Right, times the 150. All right, so that's going to get us a value of 21,900 joules. All right, so that's your amount of your heat. Then it says, calculate the minimum mass of the CaO that the student would need in order to generate this heat. All right, so we want to figure out our grams of CaO, and what we have is joules of heat. All right, and the info that we have listed up there. Yun, any thoughts on how we might get ourselves our grams of CaO?
No.
All right. How about Alexandra?
Could you do like a bracket problem?
I like it. We can do a bracket problem, right? Because we have an amount of heat in joules, and we have an equation with a delta H, so we can do a bracket problem. All right, so we're looking at 21,900, all right, joules. All right, let's call that 21.9 kilojoules, right? Because it's going to have to be in kilojoules to use our equation up there. All right, so we've got that much kilojoules. We need to convert kilojoules into moles. All right, and I'm going to keep with that theme I've been showing you guys, and you don't have to do it this way, with that whole moles of reaction, right? So that terminology matches, right? So you have right there that it's 63.7 kilojoules per 1 mole of reaction. And remember, the reaction is just the entire equation. So you can mole-to-mole ratio a mole of the reaction to any substance in it, for instance, the CaO, by saying 1 mole, one time the reaction occurs, whatever the coefficient is, a 1 there. All right, so I didn't really teach it that way. I always just said, hey, it's the kilojoule number per whatever the coefficient is of the substance. And the reason that is, oh, we're really doing kilojoules to mole of a reaction, then the reaction into moles of the substance. So that might help clarify things for a lot of you guys. All right, and then they wanted mass. So we got to go moles CaO to grams. All right, so your CaO is going to be 5608. And if we do that, 21.9 divided by 63.7 times your 56.08, it looks like 19.3 grams of CaO is needed. All right, questions on that one?
So the moles of reaction is the coefficient in front of all of them?
Yeah, so it's just 1 with mole of reaction, and then whatever the coefficient is for the mole of the substance. So it's just like any other mole-to-mole ratio. Right? Okay. It's just the mole of reaction is always going to be 1.
Okay.
Other questions on that guy? Okay. All right, so into letter B. All right, so B says, the student hypothesizes that the design of heating a pad could be changed to enable it to heat 150 grams of water from 25 to 90 using a greater mass of the CaO, right? And it says use the data below to determine the standard entropy, delta S, in joules per mole K for the reaction, and it lists those things in the table. All right, so Camille, any thoughts on how this data can help us get a delta S?
Is there an equation?
There is, and it's the same equations that we can use for delta H. So what are our versions of getting delta H? Right, Q stat, but it's not that.
Bonds broken minus bonds formed, or products minus reactants.
Okay, so we can do bonds broken, bonds formed, products minus reactants. This guy here doesn't say bond energies, so it's not that. So this is feeling like a products minus reactants deal. And just remember, your coefficients matter when you do products minus reactants. All right, so we go ahead, and our products are the CaOH2, right, which they told us was 40, minus the reactants, which was 1H2O, which is 70, and 1 CaO, which is 83. All right, so we do the math on that. And it looks like we had negative 113 joules per mole Kelvin. All right, questions on that one? They didn't ask this question, but they could. Be ready. Ethan, if they asked you to explain why is the delta S negative, what would be your thoughts there?
It's decreasing in microstates.
Agreed. Look at your equation and tell me why.
Because it's going from 2 moles to 1 mole. I mean, no. It's going from a solid and a liquid to a solid.
Good. So that would be the driving one, right? It's a liquid going to a solid. That decreases microstates. But you weren't wrong either, right? If you didn't catch that, 2 moles to 1 mole decreases microstates as well. All right, so that's good work there. All right, II wants to know, is the reaction thermodynamically favorable, all right, at 90 degrees, and assume that delta S and delta H are constant in that temperature range. All right, so if I want to prove it's thermodynamically favorable, all right, Carmen, give me some thoughts on what that means to you when they say thermodynamically favorable.
I don't really know.
All
I don't
right,
really remember.
that's okay. All right, how about Angel? What's thermodynamically favorable mean to you?
Negative delta G.
There we go. Yeah, don't overthink it, right? Thermodynamically favorable just means a negative delta G value. All right, so if we can get ourselves a delta G, we can prove it's thermodynamically favorable or not. All right, take over from there. Rocco, do you know an equation that solves for delta G based on some of the stuff we have?
I'm not sure.
All right, and when in doubt, this is what you do on the real test. Go up to the equation sheet. Right, this stuff has to do with thermodynamics, so I look into this section and start spotting. Do you see an equation that tells us delta G and links to the data that we have already?
Yeah, the delta G of products minus reactants.
So I like that for the last one, right? Because those numbers were the delta S's in that table, not your delta G's.
Oh, okay.
So you have a delta S from letter B, and you had from the equation a delta H.
So the delta G equals delta H minus T delta S.
That's the one. Okay. All right. So we can solve for that. All right, the delta H they gave us was the negative 63.7. All right, minus T delta S, and they said at 90 degrees Celsius, but be careful. What do you have to do to that temperature? I'm sorry, I don't want anybody else. All right, so you got to make it Kelvin. So 363, and delta S there is in joules per mole K, but all this has to be in kilojoules. So you got to make sure you call that negative 0.113. All right, so you do your math on that. All right, negative 63.7, right, minus negative 363 times 0.113. All right, so if we do that, we get a value negative 22.7 kilojoules per mole. Our delta G is negative, so like Angèle said, yes, we would be thermodynamically favorable, right? And you support it with that calculation. Questions on that first part? Okay. All right, scrolling down. A little bit of a shift of gears. It says the student learns that CaOH2 produced from the reaction is relatively insoluble and dissolves in water according to the equation below. It says the student preps a saturated solution and determines that the Ca plus 2 is 0.011 molar. Calculate the value of KSP for the reaction list. All right, so we've been doing a fair amount of these lately. All right, Abby, in your humble opinion, what is a good way to get K?
An ice table.
I agree. So we want to do an ice table. So we've got our equation. All right. Abby says we're going to go I, C, E. All right. Like take over from there. Mia, what are you going to do for the CaOH if it's a solid?
You will put the 0.011 molar in there. Oh, if it's a solid, no, never mind. Okay.
Yeah, solid, you just dash it out. What's our initial of Ca plus 2?
0.0.
Yep, don't overthink it. At the beginning.
Is it nothing? Okay.
Yeah, it's 0 and 0 to start. Now walk me through my change line. All right, what's this going to be?
Minus x. Oh, or x and then a plus 2x.
Okay. And then that just repeats in these guys. All right, so then we'd have to plug it into our K expression. All right, Carmen, help me out with that. What would be your K expression for this guy?
K equals OH negative squared and Ca plus 2.
Okay. All right. Now go ahead and plug them in, Carm. The OH negative is what?
The OH negative is 2x and the Ca plus 2 is x.
Okay. All right. Now talk me through the math there. All right. Yun. All right. If I square this, what's going to happen?
4x squared.
4x squared times x means?
4x cubed.
Good. So 4x cubed equals the KSP. All right. So I got to this point, and it wants the K value, and I don't know x. What's always true when that happens, Shane?
They have to give you some sort of other data.
What do you think that other data is?
They give you the concentration for the Ca plus 2.
And what is it?
Is that the X?
That is, right? Because if you look at your table, Ca plus 2 being 0.011 0.011 is X. If that were the OH negative value, you'd have to divide it by 2 for the X. All right, so we're just going to plug that in. All right, 4, all right, times the 0.011. All right, cube. So cube that number first, 0.011 times 0.011 times 0.011. All right, then times that by 4. All right, and if you do that, you're going to get a value of 5.3 times 10 to the negative 6th. All right, questions on that one? Okay. All right. So it says the student wishes to significantly increase the solubility of the CaOH2 and has access to the following substances: all right, distilled water, CaCl2, KOH. Hang on one second. Hey, what are you doing? Oh, yeah, do that on the back porch, please. Sounds like an elephant coming through the floor. Thanks, Scarlett. Okay. Could you guys hear that giant thud?
Yeah.
Through the microphone? Okay.
Yeah.
Yeah, so turns out it was my daughter popping bubbles from a delivery package on the kitchen floor by jumping off a chair and landing on it. So.
Oof.
She has strategy.
Is that Elena?
It is.
Oh, you snuck in, you cheeky. All right. Sorry, I can't say the second part of that.
Well, what's the second part?
I'll tell you when you're older.
I am older.
All right, when you graduate. All right,
Yeah.
so it wants to know who can we add that's going to increase the solubility most significantly, and it's based on equilibrium and Le Chatelier. So they're really hinting at you what you should be thinking. So let's start simple here. All right. Angel, what's the soluble side of the equation up here? Right, like which side's the dissolved side?
The reactants.
Careful, what's the tag on the CaOH2?
Oh, I mean the products. Sorry.
The products, okay. So when they say I want to make this more soluble, that's code talk for I want this equilibrium to shift which way, Angel?
Towards the right.
Towards the right, exactly. Because I will make it more soluble if we shift toward the ions. And there's a variety of ways we can do that. All right, Elena, what are some things we can do that would make this shift right?
You could increase the amount of reactants.
Usually increasing the reactants would shift us right. So did I have CaOH2 at my disposal? I didn't. So that's no good. All right, what else?
If it's endothermic, you could add more heat.
If it was endothermic, we could add more heat, but they didn't give us any info about that. All right, so nothing there. All right, so you took care of the stuff that we could add, right? What's the other way we can get it to shift?
You could take away some of the product.
There it is. So if we can remove some stuff on the right, it'll cause a shift right. All right, take over from there, all right, Alexandra. All right, if I add, let's start with this one, CaCl2, all right, I'm adding Ca plus 2s. Which way will it shift?
Oh, shift right.
Careful, I added on the right.
Oh, so shift the opposite direction.
Exactly, so that's no good. That would make it less soluble. So this guy here adding CaCl2s, that's going to cause a shift left. So that's no good. All right. If we add KOH, right? Adding KOH is really adding OH negative, right? Because that's soluble. All right. Camille, what's adding KOH going to do?
The Ca is gonna bond with the OH, so then there will be less Ca and it will shift right.
And careful, OH is on the side, though, that you're adding.
So then it'll just increase OH.
It'll just increase OH, causing a shift which way?
Left.
Left. So that's no good. All right. So we cross this one out. All right. This one here, if I add distilled water, all right, take over from there. Abby, what's adding distilled water do to our stuff?
It's gonna like make it dissolve more.
Yeah, it's gonna like cut its molarity, right? Right. So that's decreasing this, right, and decreasing this. All right. Will that cause a shift right?
Yes.
Yes, it will. So that's fair game. Right? Adding the distilled water, it should do that. Right? And then lastly, we have HCl. If I add HCl, it doesn't look like either of those is in here. All right. But, right, sometimes something that you add will affect the equilibrium. All right. Ethan, can you figure out what adding HCl affects over here?
Would it affect the OH negative?
It sure would, because HCl is a strong acid. What's it going to do?
Add H pluses.
And that's going to make what happen to these guys?
Waters.
Yeah, so it's going to take away a lot of OH negative. It's a strong acid. Okay. All right, so that one is going to have the greatest effect because it's going to remove the most OHs. All right, this is going to cut the molarities, which will have an effect, but nothing compared to removing something. So you guys would want to say adding HCl would increase the solubility because it would remove OH negatives, causing a shift to the right. Questions on that for you guys? Okay. All right. So then wanted to do number 6 and number 7, which are both short answer. All right. So here's number 6. Propanoic acid, C2H5COOH, is an organic acid that's a liquid at room temperature. An incomplete Lewis diagram for propanoic acid is provided in the box below. Complete the diagram by showing how the remaining atoms are arranged, all right, around that carbon with an asterisk. Your structure should minimize formal charge and include any lone bonding pairs. All right, so they basically just want us to finish this picture. All right, so if we're going to try to finish that picture, all right, Rocco, talk to me about what you would start doing with, well, let's start simple. What is it you still have to add to the picture?
The O's.
Yeah, 2 O's and right. So we got our 2 C's, we got 5 H's. That's what they showed you here. Then it's COOH. So what else do you have to add?
Another C.
No, you got it. So right, ready? 2 C's, 1, 2,
Yeah.
5 H's, 1,
Yeah.
2, 3, 4, 5. There's the C. We just have to add the rest.
Oh,
of
another
it.
H. Another H.
Yeah, we got to add the OOH. All right, so this here is a sneaky way of them putting a little bit of organic onto the test. And I always make sure that we go through these when we do our Lewis structures. COOH is like a signature. All right, so when you see that, that's the signature for a carboxylic acid. It's an organic acid. All right, so that always looks like this: an O, an O, and an H, right? So when you see COOH, it's talking about a connection like this. right? Do not do this. Okay, it's not going to be that. That's not what COOH means. It means that both O's are off the carbon. All right, so if you guys see that, you'll know what to do with it. Okay, but we still need to make the picture be right. All right, so we got to get our electron bank. All right, Elena, talk me through the electron bank for the whole thing.
So there's 2 O's, which would be 12.
Okay.
There's 6 H's, so that'd be 6.
Okay.
And there's 3 C's. Is that 4?
4 each.
Okay.
For 12. For a total of
30.
All right. 30 in the bank. Take over from there, Alexandra. All right, how many did we burn up with our connections?
20.
Good. Leaving us with
10.
10. All right, so we have 10 dots to put on this guy. So we're going to work our way from the outside in. All right, Carmen, take over from there. Should the H get any?
No.
No. How about the O?
Yeah.
How many?
2 on top, 2 on the bottom.
Okay. So there's 4. I have 6 left. How about the O up here?
Yeah.
How many?
The rest.
The rest. 4, 5, 6. All right, so my bank is empty, and then I look to see if everybody's happy. All right, take over from there. All right, Shane, is everybody happy?
No,
All right, who's not happy?
the 1C is not happy.
All right, this guy right here. How do you fix it?
You can take one of the pairs from the O above it and just put it on and make a double bond.
Good. All right, and listen, Shane is absolutely right. It's the O above it because it said you should minimize formal charge, and that means all zeros. So if you did this and made the double bond down here and the single bond up here, like take a look. That O is 6 minus 7. It's a -1. This O is 6 minus 5. It's a +1. That's bad for all sorts of reasons. 1, it's not all zeros, so that's crappy. And 2, we would never have a positive formal charge on the highly electronegative O. But if you do it for this guy, 6 minus 6, 0. 4 minus 4, 0. 6 minus 6, 0. Everybody zeroes out. All right, so there's your picture. All right. So sometimes people just remember, like carboxylic acids always look like that. Double bonded OH. Right. So if you see COOH at the end of a carbon chain, it's always going to be that at the end of it. Always. Okay. So then the next question builds off of it. It says, identify the hybridization of the carbon atom marked with the asterisk. All right. So that one is this guy. Right here. If I want hybridization, all right, Yun, what do you have to do?
So see if there's dots or bonds around the atom.
Good. So how many areas of density for this guy?
3.
Yeah, 1, 2, 3. All right. 3 areas of density corresponds with what hybridization, Yun?
SP2.
Good. SP2. Didn't ask it, but let's go ahead and do it just for practice sake. Camille, what would this guy's record be around this carbon?
3O.
And 3O, do you remember it?
Is that trigonal radical?
Close, trigonal, planar, and that would be bond angles of 120. And that's a sheet I would have out for the test as well for you guys, right? That's in your chapter 8-9 notes. There's a big old table that says the record, the geometry, and the bond angle. I don't think they're going to ask it because it's stuff you could look up, but you never know, and you might as well have it at your fingertips, all right, if it's there. All right, so that's what's going on in B. All right, in C, it says propanoic acid has a lower boiling point than butanoic acid, right? It says identify the IFs present among the molecules in propanoic acid, which is the guy that we drew up here. All right, so if I want to list the IFs, Abby, what do you think we should do?
You should like go through each one and figure out like what it has, like London dispersion and then dipole.
All right, so what do you think?
Well, it has London dispersion,
Good, because everything does.
and then it has dipole because of the OH at the end. Like it's not nonpolar.
Good.
And then it has a hydrogen bond because of the O with the H.
Good. Right, and you don't have to list both of those, right? If it has a hydrogen bond is a really strong dipole. So just think this guy knocks this guy out. We don't list them. All right, so we have hydrogen bonding. We have London dispersion. Other ways, remember refreshers on these. In these long carbon chains, if I want to look at even or uneven pull, splice it in half down the middle and see if it's symmetrical. Like, is it the same above the line as it is below the line? If the answer to that question is yes, it's non-polar. All it has is London dispersion, which is why all what I just call hydrocarbons, like if they're all H's, right? If they're all H's, when you splice it down the middle, H is above, H is below, it's non-polar, right? But that double bonded O up there, right, and the OH at the end makes it have a hydrogen bond. All right, so that's good stuff. It just wanted the types of IFs present in the propanoic acid. All right, then it says, which of the following types of IFs that you identified in part C is most responsible for the difference in the boiling points? All right, so we didn't draw it, but let's conceptualize. All right, Mia, if I did the butanoic acid, which was this guy, C3H7COOH, what's going to be the difference?
It's gonna have a little bit of a longer carbon chain, but
Exactly.
it also have the same thing on it.
Right. The only difference there is what I'll add here and say the red, right? It's going to have another carbon in the chain with an H above and an H below. All right, so that's it. All right, Mia, is that going to change its London dispersion?
No.
Right, it'll still have it. Is it going to change the fact that it has hydrogen bonding?
No.
No, right? Because they both have the COOH. So they both have the same forces. And what's the phrase we always use, Mia, when we want to explain why one's more than the other and the forces are the same?
A more polarizable electron cloud.
Good, right? That extra carbon and two hydrogens makes the chain longer, which means it can wiggle more and it means it's heavier. That's a more polarizable electron cloud. So you would say, what types of IFs did you identify that are most responsible? You would say the London dispersion and more polarizable electron cloud would be the main reason. Questions on that one? Okay. All right. Last one for the day. All right. It says a student has 100 milliliters of 0.40 molar CuSO4. They need to make 100 milliliters of 0.150 molar CuSO4 for a spectrophotometry experiment. All right. That's the kind where you shoot a beam through it and we see how much it absorbs. All right. The following lab equipment is available for preparing the solution: a balance, weighing paper, funnel, 10 mil beaker, 150 mil beaker, grad cylinder. Uh-oh. Hang on. I got a crying girl coming in. What happened? Mama's working. Come see me. Hang on, guys. I'll be back. Okay, we're good. Little scooter incident. All right, so it wants to calculate the volume of the 0.40 molar required for the preparation. All right, so we've got a volume and a molarity of this guy, and we need to make a volume and a molarity of this guy, which is the same somebody, and they want to know how much of the more concentrated stuff do we need. All right. Elena, any thoughts on what type of problem this is?
Not really.
Yeah, it's a little sneaky one. Anybody think they spot it?
M1V1, M2V2.
Yeah, it's a dilution, right? The only time we get two molarities of the same substance is in a dilution problem. So this is an M1V1 equals M2V2. All right, so we know that we want to make 100 milliliters of the 0.15 molar. We have 0.400. We need to figure out what volume of that do we need. We know we have 100 mils. The question is I don't know if we'll need it all. All right, so we take the 100 times the 0.150 divided by the 0.400. All right, so that means we're going to need 37.5 milliliters of the concentrated stuff. The other thing I'll see is they will ask you, oh no, it's coming up right here. Don't worry, we're about to answer it. All right, so that's A. All right, now in B, it said, explain to me how you would prepare that from what you did using the equipment. So if you need a refresher on this whole like steps to making a dilution, all right, go into chapter 4 is where I think we did it first, and then we did it again in 14. And look for your dilution stuff, and it'll do all the step by step by step. But we'll do this one here. All right, so be careful if it's acid, right? It's always acid to water, right? Like you ought. But let's start simple. All right, I know I need 37.5 milliliters of the concentrated CuSO4. That's the 0.40 molar. And I know I need 100 milliliters total. Right? So that's hiding something. Right? The difference between the 37 and the 100, anybody know what that's hiding? Or it's not listing, rather? Right? Like if I subtract the 37.5 from the 100, what's it going to tell me?
How much water?
How much water, right? So that's the part that a lot of times they will not flat out tell you. So I know I need 62.5 milliliters of distilled water. All right, so remember, if we're prepping solutions, all right, you always want to use a volumetric flask. All right, so I'm going to use the 100 milliliter volumetric flask. All right, that was on my list of things right here. Now, all right, I have to decide how to put that stuff in there. All right, so the first thing that we want to put in, right, is the CuSO4, right, the substance, and then we'll dilute it with the water up to the line. All right, so how are we going to deliver the 37.5 milliliters? All right, so we start looking at devices we can use to deliver 37.5. All right, so will we need a balance? Right, am I going to need a balance or weighing paper?
No.
No, when would I need that?
If you wanted to filter out solids.
Yeah, if I was starting with a solid, then I would use the balance and the weighing paper, get the solid and put the solid in, right? But we didn't start with the solid, so that's why I'm not going to use these. All right. All right, we've got a funnel, a 10 milliliter beaker, a 150 mil beaker, a 50 mil grad cylinder, a 50 mil burette, and distilled water. Like, given your sig figs here, one past the decimal, like, what is the most appropriate glassware to deliver the 37.5?
The grad cylinder.
grad cylinder, right? The grad cylinder reads to one place past the decimal, so it would have the accuracy needed. So I'm going to use the grad cylinder to measure out 37.5 milliliters of the 0.40 molar CuSO4, and I will transfer that into the volumetric flask, and to be safe, you can pour it through a funnel. Right? And then you would take a grad cylinder again, all right, and you would get 62.5 milliliters of water and pour it in, and you'd have to break that down into 2 steps, right, because it's a 50 mil grad cylinder. All right, and we need to add 62.5 milliliters of it. So you would say add 50 mils of the grad cylinder, then add 12.5. Right? I'm not going to use the beakers because they just don't have the accuracy. Right? The beaker is estimating to the ones. Right? I can't be sure of this 0.5 or this 0.5. So it's got to be a grad cylinder. And then you'd say cap and mix thoroughly. Questions on that, like solution prep? Okay. All right. Finishing out the day. It says the student plans to conduct a photometric analysis to determine the Cu+2 in the solution. Solution has a small amount of cobalt nitrate present as a contaminant. Students given the diagram below, it's the absorption curves for those 2 substances, right? So here's our wavelength. Right, here's the absorbance, all right, and they absorb at different wavelengths because they're different colors, right? Cu tends to be blue ion, the cobalt tends to be an orangish ion, so they're going to absorb at different wavelengths of light. So it says the spectrophotometer available to the student has a wavelength of 400 to 700. What wavelength should the student use to minimize the interference of the CO+2? So I don't want to detect the CO+2, but I do want to detect the copper. All right. So talk to me, Ethan, about what your thoughts are on what we might want to do there.
Would there be an equation in the equation sheet for this?
No, you can just use the graph, right? The graph has wavelengths on it. So you want to sense the Cu+2s and absorb those, but you don't want to absorb the CO+2. So what wavelengths do you want to kind of focus on?
Around 800.
I agree, right? So we want the Cu+2 to get detected, but not the CO+2, right? So we want something up here like north of, I'd even say you're okay above 750, right? So you just want to get away from this cobalt, right? So that the cobalt is down, not getting measured anymore. And that all starts right around like the 750 range. Okay. And that was it, right? It seemed like kind of a complex question. And it was just look at the graph. Where do we detect Cu and where don't we detect this? It's up in this range, right? Pick the value up there. All right. Questions on any of those for you guys?